We'll talk about this one next. Okay. Okay. Now, first, I have to apologize for what happened. I don't know what happened, but the folder should be open on the 20th. I discovered today by 4:30 it was still closed. So I updated the file and have to make a new file for the week 2 lecture. If you had a look, you will understand that what we're going to cover today is going to be the pin and the silos design. So I think you have seen these things before everywhere. And actually they are missile silos. They, they used to store the materials which cannot be simply stored uncovered. So we said there are two types of the storages. The first one is the outdoor storage. Simply you can pile the material uncovered, or you have to use the confined one. For the outdoor storage, where you're going to have a core storage is going to be stored outside in large piles when the hundreds of thousands of tons of the materials are going to be involved. The outer storage can be affected by the environmental problems such as the dusting or the leaching of the soluble material from the piles. And dusting control by covering the piles is going to be the only solution we're going to have. And leaching can be controlled by covering or by locating it in a shallow basin. So that the cold storage usually is going to be in big piles, no need to be covered, most of the cases. And the same thing for the sand and the gravel storage. The other type is the confined storage. Usually, something that will be consumed later is shouldn't left in the open area. So the solids that are valuable and can be affected by the environment in outdoor piles are going to be stored in pins or hoopers or silos. So now we have pins and silos because actually the hooper is part of the pins and the silos. So the storage for the bulk solids come in all shapes and sizes. This can be with the flat bottoms, this can be with the pyramidal hoopers, with the conical hoopers, with the wedge hoopers, and with the transition hoopers. And some are going to have one outlet, other may have two. Of course, I think most of you went through the near the fish market. There's the cement factory there, and you can see that they have already some silos. Most of them have two outlets. Some may have several outlets to increase the flow rate when you try to empty the silos. So pins and hoopers are used for the storage of the bulk materials during the material handling process. So sometimes you don't use it to store the material for a long time, but for example, if you want to feed a screw conveyor or build conveyor, you may need the bin and hooper. So you just fill it, then you're going to empty it from below to feed the system. The hooper is the lower table section of the bin, and which can be used also found above the feeders in the gravity reclaimed stockpiles. Both must be designed for the actual bulk material being handled over the entire range of the operating condition, including the varying characteristics. Hoopers must be designed such that they are going to be easy to load, and more importantly, the hoopers must be designed such that they are going to be easy to unload. Because you remember the flow types we had in the bin and the hoopers, so we're going to talk about this one in more details today. So these are the silos, which are bigger than the bins. Silo is storage structure for the storing of the bulk materials like the storage of the grain, the coal, the cement, food products, and other types. Silo is tall usually, and relatively its height is going to be much more than its diameter, unlike the bins. The types of the silo can be either cylindrical or have a conical bottom. An example for that is the farm silos. You can see that we have different storage volumes, different diameters, and other properties like the material we're going to use for. I don't want you to go through this one probably. So in all the cases, for this one, for example, it's used to fill the screw conveyor we have here for loading the trucks. So that's the outlet where we're going to have the screw conveyor inlet. The motor is going to be at the top. This one is the flexible screw conveyor, so we can simply move it and control it in different directions. That's the plotter and the farm installation for the silos. And this is an example of the silos. Usually it's going to be made of the stainless steel. Usually it's going to be different pieces which are going to be assembled together. And this is another example about the structure we can have for the supporter. Okay, that's the bottom silo, which is very popular in the case of the grain stores. Construction of the silos, usually we're going to use stainless steel or corrugated plates. The construction of the silo, first you start from the roof, as you can see here, then you start to go up until you finish the whole structure. Now, does that remind you of something? Which other, well, this will be a different thing, but it's related to the material handling. What the other structure in the material handling, which usually start from the top, then you start to push the things up? Cranes. The cranes. Okay, have you seen how they install the cranes? They usually start with the top part, then start to take the columns one over the other until we're going to have the proper height. Okay, so they start the roof, then start from the top to the bottom, and the top sheet thickness is going to be less than the bottom one. Now, why the bottom one is going to be thicker? The load is going to be, the pressure load is going to be higher at the bottom. Something like if you study the fluid dynamics, usually if you're going to have a bar, okay, or a tube, usually the pressure at the bottom is going to be higher than the one at the top. And we're going to have an example for that as well. For the okay, and typically it's going to be for holding the dry matters such as the powder or the grains, and usually the bins is not going to be storing the material for a long time as the silos. Bins may be round or square, and round bins tend to be empty more easily due to the lack of the corners. And the stored material may be a powder, as seed kernels, or as popcorn. The hooper is going to be the lower part of the bin, and usually we are going to use this one to empty the bin. So this can have different shape. As a small vessel with the sloping bottom for the temporary storage before we are going to feed the solid to the process. And it's going to be filled to the top, and discharge is going to be from the base, as you can see here. Sometimes the hoover may be vibrated externally to encourage the flow, because we talked yesterday about the build-up of the material on the wall. Okay, so the vibration is going to be the best option to empty it faster. An angle of the slope is going to be usually more than the angle of the repose of the material we're going to have. That theoretically, but actually in the process of the design, we're not going to use the angle of the repose. There's something like what they call the rule of thumb. You have to know what the angle of the repose of your material. Then you are going to choose that the angle of the slope of this side should be higher than the angle of the repose. That's once again that the rules of thumb. So if you have a silo, or you have a bin, sorry, with the hooper, and they ask you to use this one for storing a certain material, you have to check the angle of the repose, then do that. You don't design anything. Then you say, okay, now this will be suitable or non-suitable. The hooper design background, well, actually, that's how the bin started to be at the beginning. Just a cylindrical building, and they start to store the things at the top and empty it from the bottom. And usually that's what was happening. They didn't have any standards for that. So at any time it may collapse due to the load we have inside. The pressure has got to push the walls, and the things start to collapse. So in 1950s and before, The storage bins were designed based on the architectural point of view, how nice it looked like. So Jinky, the same person who had invented the test of the shear test for the material, developed the theory and methods to apply for the design of the bins. So Jinky related the material stored to the design of the bins, hoopers, and silos, and he sets in equations and measurements of the particle properties. So that's why we had the lecture for the particle properties and characteristics in the first week. Because everything we're going to do from now on, we are going to call back the characteristics of the material we're going to use. Well, except in week 4, because we're going to talk about the AVG, which is something for the unit load material handling. So these are the example for the old designs. It's tough to use it anymore. Okay, now Carl Jacob, which is another person back in the 60s, he was working in parallel. This guy, Jinky, was in the United States, Jacob was in Germany. So actually, Dr. Peter Wopich, who is going to be your visitor lecture in week 5, he will tell you about the two schools we have in the material handling and storages. We had the American school and the German school. They tried to unify the things. They didn't get anything yet. Now, even you can see that most of the units we are going to have is going to be either in the SI unit or the IP unit. Till this moment, nobody could unify the units. So Carl Jacob asked this question when we start to design the bins. First, what are the appropriate flow mode you would like to have? What are the hooper angle we are going to have? What is how large the outlet for the reliable flow? And what the type of the discharger is required, and what is the discharge rate you would like to have? So by finishing today's lecture, you'll be able to answer actually all these questions. So when the hoopers are going to be designed without consideration of the actual materials being handled, the problem eventually is going to arise. For many materials, the flow problem can be eliminated by simply ensuring that the massive flow pattern exists in the vessel. So if you are going to enter it very easy, very fast flow, then you're not going to have any actual problem in the system itself. So the first step achieving the massive flow is to ensure that the converging walls are going to be steep enough. So you don't have the wall less than 45 degrees because this will cause a problem for you. Usually you're going to take it higher. Steeper is better. And it should have a friction low enough to allow the bulk materials to slide along them. And some types of the pins we have, and especially this will be in the case of the powder, they call it the smooth wall pins and silos. That the shiny one if you have seen one before. And this is going to be accomplished by first testing the material again to store, to measure the wall friction, and then calculating the minimum hooper angle that will be allow the massive flow to occur. Now, if you remember the term massive flow, that means the flow rate at each point in the silo is going to be the same. And this is the what they call the comprehensive target for our design. So the hooper flow modes, as we mentioned earlier, are the massive flow, the funnel flow, and the expanded flow. In the massive flow, that's something we're recalling from the lecture number 1, when all the materials in the hooper is going to be in motion at the same time, but not necessarily at the same velocity. For the funnel flow, the centrally moving core, so everything is going to flow only from the middle, but the things on the outside is going to be at static. So it's either going to be dead or no moving annular region is going to occur. So what we're going to finish with, a hole in the middle, and that's what they call the rat hole, because I'll show you, it's actually going to look like the rat hole. And we have the expanded flow, where the massive flow cone with the funnel flow above it. So everything is going to be from the below, but at the top is going to be static, and that's what what we call the arcing, for example. So that's the massive flow. Everything is moving. All material move in the bin, and including the near the walls. In the funnel flow, what's happening that the material move in the center core only, with stagnant material is going to be near the walls. In the expanded flow, a combination of the massive flow and at the center, and at the exit of the fuel flow is going to be the pin above the hooper, normally used for the installation. So what's happening, we're going to have built up material, and that's usually happen if you are going to store the material for a long time. So we call it the time consolidation, when things start to build up due to the humidity, for example, or due to the pressure and compression due to the weight. So this is more a clear view. Okay, so that's what's happened. You can see this is the massive flow, this is the funnel flow just in the middle, and that's what's going to happen in the expanded flow. So we're going to have the built up material on the side. So what will happen if we are going to have improper design? Well, simply we can say we are going to have a disaster. One of the disasters actually happened, for example, back in the 30s, or I don't remember, maybe 30s or 50s, in the United States, where there was sugar factory. So they making what they call the black honey, which is taking the sugar cane, extract the sugar, so it's going to be soluble, black color, and as usual it's going to be hot. So they start to store it in a silo. Improper design caused the silo to collapse, and many people died because it was hot solution covering the building to the height of 1 meter. Actually, the neighborhood around the building. I may find something on the net and show it to you during the lecture. So the poorly designed silo is the natural outcome of the inadequate understanding of the solid being stored in. So 5 possible conditions will occur as a result. First, we may have no flow. Second, we are going to have the erratic flow. We may have the flooding, the counter-current airflow, and the segregations. The segregation, the build-up of the material on the wall. The clearly no flow condition negatively affects your process. If the material is stuck in the bin, this will be a problem. Everything will stop and you have to make it flow. There are, well, actually, an improper way to make it flow, force it to flow. As I told you last time, when the people start to knock on the wall from the outside, and actually what's happened is that you are going to lose the smoothness of the wall, and this will create further problem. Or we can simply have another advanced method, like using the vibrators, the shakers, or simply blowing the air inside. And again, to post a video about that, because actually it shouldn't be a lecture by itself. So the condition can occur when you try to initiate the flow by opening the gate or starting the feeder, then nothing will come out. Okay, now these are examples that no flow happening. The material start to store in for a long time. So what happens is that the segregation start to happen in one area. Is going to be more than the other area. So the weight is going to be unbalanced inside, and these things start to collapse. Okay, so the reason for that is the wrong discharge, silo will get damaged. Okay, this is another example for what's happening. As you can see here, actually we can simply have a side discharge system. So if the things start, well, we couldn't have the thing. Well, actually, usually we don't get to have this problem in the flat bottom silos, because we have the device which is going to simply mix the material inside and force it to come down. But I think in this case that if you are going to store it for a long time, we're going to have the segregation of the material at the top. So you have to move the material from different levels to get the flow. So these are the problem with the hoopers, as we mentioned earlier. What's happening is either we are going to have the arcing from the top or the bottom. The arcing in the bottom is going to be the most problem, because something like going to have something like the dome, which will prevent the material from flow. The piping or the rat hole, the slobbering, the erratic flow, the flushing, the inadequate flow, the structural blockage, the structural retarded flow, and the segregated flow may occur. So these are the main problems. I'm going to talk about most of them in this lecture. So the rat holing and the piping, as we mentioned earlier, the flow is going to be mainly in the middle, bit up on the side. The funnel flow, the arcing and the dooming, the unsaturated flow, like the slobbering, the flushing, when everything is going to go to the sides, the adequate empty, where most of the material is going to stuck inside the bin, the mechanical arcing, and the most important problem is the time constellation, or what we call it as the caking, where the thing starts to solidify due to the long time storage and the effect of the humidity on it. So the rat holing and the piping occurs when the core of the hooper is going to be discharged. But the stagnant sides are going to be stable enough to remain in place without flowing, leaving the hole down through the center of the solid stored in the bin. So that's what we're going to see from the top. In the segregation problem, we're going to have the coarse material is going to be concentrated on the side, and they're going to hold each other because they are going to be coarse, while the fine material is going to flow in the middle. So that is segregation. Different size and densities of the particles tend to segregate due to the vibration and the percolations actions of the small particles moving through the void spaces between the large particles. The arcing and the dooming, when no flow is going to occur because we are going to have the cohesive arc while preventing the material from exiting the hooper. So as I told you, something like the doom, and actually the basic theory of the doom that is going to take the high pressure and prevent it from flow. And that's what the theory of you cannot break the egg by standing on it because it's have an arc shape. The incomplete emptying, where we're going to have the dead areas in the bin that can prevent the from complete discharge of the material from the bin itself. The unsaturated flow, where the flow is going to be too slow and the material does not exit from the hooper fast enough to feed the flow of the process. That's a problem because either the outlet is going to be too small, that's something you have to design. What we're going to learn today actually is to design the minimum outlet diameter. That means you have to go larger than this one. If you are going to be less than the minimum, you're always going to have the insufficient flow. And also the other reason is that the material is not sufficiently permeable to permit the dilations in the conical sections, and we're going to have the blow flow. That means it's going to be by small amount each time. The flushing problem, usually we're going to have the emptying device. And in this case, it's trying to send backward to the system. And this is one of the main problems, and usually is going to occur in the system of the pneumatic system. We're going to learn about that in week 5. So the flushing will occur when the material is not going to be cohesive enough to form the stable doom, but it's going to be strong enough that the material is going to be discharged or slow down while the air is going to try to penetrate into the packed material to loosen it up from the material itself. The resulting is going to be the sluggish of the solid as the air is going to penetrate in a short distance, freeing the layers of the materials, and the process will start to over with the air penetrating into the freshly exposed surface of the material. Now the flushing, once again, as you can see here, so what's happening that the air is going to go up while the solid tries to leave, and that's what we are going to have at the end to be solved by simply sending the pressurized pneumatic system from the top, and this will prevent the air from going up. Everything will go down through the what they call the live ground, going to take the flushing out of the feeder. Now the mechanical arcing is akin to a traffic jam of the outlet of the bin, where too many large particles is going to be competing from the small outlet. So the arcing, they are going to stuck together the bigger material and stop the material from flow. So usually if you're going to have 6 multiplied by the maximum diameter of the material is going to be the minimum outlet size to prevent the mechanical arcing, and 8 to 12 multiplied by the material minimum diameter is going to be preferred for the preventing of the arcing process. Now for the caking and the time, which is the time conservation, and that's what you have in the question number 2 in the assignment, when we have 2 different equation for the material density. So many powders will tend to cake as a function of time, the humidity present, the pressure of the material on itself, and the temperature. So this is a relationship between the time and the shear strength, and that's relationship after a certain time. So the caking is going to be simply increasing the shear strength at a certain time period to be the maximum.
Can you go one step back?
One back.
Again, what is
The diameter. Okay, now that's something you're going to do next week. Next lecture, we don't have a lecture here. We have to go to building 11, basement number 4. So let's have in one of the experiments we're going to have, if you remember when we talked about the shaker, the sieve shaker. So we're going to have a multiple diameter, then we're going to check what will be the average diameter of the material particles. Okay?
Yeah.
So what's happening is that this is the particle maximum diameter, dp particle.
The one that we're going to find in the first sieve.
Yeah, the one you're going to find at the higher sieve, the bigger one.
Yeah, but this doesn't matter the size of the sieve, the silo. Like for example, if you put wheat.
Yes.
How big? Like 10 mil.
Less than 10 mil.
Less than 10.
Yeah.
It should be really small.
No, yeah, not more than 4.
Okay.
Yeah. So the diameter here, we're talking about the minimum acceptable diameter.
Oh, okay.
You can go bigger than that, but not less than that.
Depends on the application.
Okay. So for example, you said that the diameter is going to be 4
Okay,
millimeters.
10 times 4, 40 mil.
Yeah, that's the minimum, but you're not going to make it as 40 mil.
Okay.
That's the
Alright,
minimum
that's
to,
like
yeah,
20
yeah,
meters.
yeah. But
Okay.
yeah, this will depend on other properties, and that's what we're going to learn today. Okay, so practically the problem for the fuel and flow silos, which are going to be infrequently emptied completely, and we're going to have the time constellation, because we're going to leave it for a long time, is going to be affected to the time. And if we're going to be, for example, near the sea, we're going to have the effect of the humidity. The size of the silo will affect on the pressure we're going to have on the bottom layer, and the temperature is going to affect, because simply we are simply like we caking something, we cooking the cake, so it's going to take water, time, temperature, pressure, and so on. So the cone angles and the chances of the Hoover massive flow are the following. So you can see that almost the minimum cone angle we should have for the Hoover should be 45. We can go up to 75. Simply if I can take it more than 75, then it's going to be a flat bottom. So 45, the cumulative percentage of the Hoover with the massive flow is going to be 0%. As we're going to go up to 75, we're going to have 70% cumulative percentage. So better flow is going to be at the steeper angle. 75, the wall is going to be higher, steeper.
But you're risking area, right?
Yeah, this will affect the area, of course. Yeah. But these are just experimental.
Yeah.
So the massive flow advantages and disadvantages. So it's not 100% good, but it's the best. So the flow is going to be more consistent. Everything is going to be emptied at the same time. The reduced effect of the radial segregations. The stress field is going to be more predictable. Full bin capacity can be utilized. And first in will first out. So whatever you're going to put in first is going to be at the bottom, is going to leave first. Now, that's not going to be the same case in the rat hole, right? Because what's happened that the material at the top will empty before the material on this side. But still, the disadvantages are we're going to have the wall width is going to be higher, especially if we're going to have a present material, because the things start to move very fast. So start to wear the wall as going to go. The high stress on the wall and more height is going to be required to force the things to come faster. Now, for the fuel flow advantages and disadvantages, so still have advantages, is less height is going to be required. But let's have a long list of disadvantages. Rat a problem for disintegration solids. First in is going to be the last out. So what you put in the bottom actually is going to leave after everything will come out from the top. The time consolidation effect can be severe. Silo may collapse, flooding, and the reduction of the effective storage capacity may occur.
So
Now,
in this case means that after this collapse, then everything goes
which
out,
one?
flooding.
The flooding? No. The thing may go to the opposite direction.
Oh, okay.
Yeah. Okay. And for the Hooper design methodology, we have two measurements, two types. Either by measures, where you have to measure the powder cohesion, the interparticle fractions, the wall fraction, the compressibility, and the permeability. Then you go for the calculation stage, where you have to check what will be the outlet size, the Hooper angle for the massive flow, and what will be the discharge rate. Now that we talked about it last week. In the lab, we will talk about the wall of fraction, and I will give you, it's going to be something like a video lab about how you check the compressibility and the permeability of the material. I'll give you some data, and then you start to do the calculations. This will not be a part of the report, but it's going to be good practice for you to know about these properties. For the powder cohesion and the interparticle fractions, once again, this will be in the lab. According to these values, after you did the characteristics of the material, simply you can recall these data and start to calculate first the outlet size of the minimum diameter of the outlet for the Hooper, the Hooper angle for the massive flow, what will be the angle you should choose to get the massive flow, and you can calculate what will be the discharge rate for the material when you're going to have full open for the discharge. So we talked about the angle of the repose last week. We said if I'm going to put the material as a pile, start to fall until it's going to be in a static. This angle we call the repose angle. So the angle of the repose, or the critical angles of the repose of the granular material, is the steepest angle or the distance or deep relative to the horizontal plane, which is the materials can be piled without any slumping. The angle of repose is not an adequate indicator of the bin discharge parameter. It was good for the selecting of the if we can use it in this bin or not, but it's not going to be used in any case of the calculating of the discharge parameter. The angle of the repose definition by Jinke himself, the guy who invented this science. In fact, it is the only useful to the dimension of the counter of the pile, and its probability among the engineers and the investigators is due to not to usefulness, but due to the ease which is going to be measured by. It's very simple. We can measure it in 5 minutes. Anyone here have any experience with the construction, civil engineering? They have something similar to that, but actually it's away from that, but it's going to be useful for you in the future. Usually, if you are going to bring the concrete by the mixer, you should not leave it more than 50 minutes in the mixer, because this will simply change the parameters and the characteristics of the concrete. So they have a cone, they fill with the concrete, then they remove the cone and check. If the concrete is going to be to a lower level, that's when you cannot use it. So it's something like the repose angle, but this will be a repose height. It should be always keep itself a stand to be accepted to be used for the casting. Now we can do the same thing actually in the angle of the repose. the cone you fill with the material, then you remove the cone, and the material start to seep, and there is going to be static. So we don't use the angle of the repos to design the angle of the hooper by any means. It doesn't have any relationship between them. The bulk solid testing, and now once again, we talked about the characteristics of the material. We talked about different methods of testing. We're going to have a review about that once again. The wall fraction testing should be done. The powder shear testing, if you're going to use the powder, which measure both the powder internal fraction and the cohesion. The compressibility, the permeability. So the source of the cohesion in the material, which is the binding of the material, where we're going to build up on each other, are the solid bridges, the interlocking forces, the attraction forces, and the interfacial forces. Now, of course, you know what the interlocking force is. If it's going to be a regular shape of the material, it may hold each other and stop itself from collapsing. For the solid bridges, we're going to have the mineral bridges. This can be the chemical reaction, the partial melting, the binder hardening, the crystallization, and the sublimation process. And the attraction forces like the van der Waals, the electrostatic, and the magnetic properties. That's usually going to occur in the case of the iron core, because it have the ferrous properties, the magnetic properties. The interfacial forces like the liquid bridges and the capillary forces between the particles. The concentration factor in the test you have to do is mass concentration following the following variables: the time, the temperature, the humidity, and other process conditions, as we mentioned earlier. Now, that's what we're going to do next week. Okay, the wall fraction testing actually is similar to the direct shear testing, but this one is going to do the in the direct shear to have two halves, and actually we checking what will be the shear force between the two layers. But in the case of the wall fraction test, we are going to check the fraction between the material and the cover. Usually the cover is going to have the same property of the silo we are going to design to. So one of the most common test apparatus in the Jenke shear tester, and the powder sample is going to be placed in the sample holder. And what we're going to use is going to be simply the sand, because once again, you may use the silo to store the sand. Previously, we used to use the small particle of the coal, but in all the cases, we are going to have the same result. The guy of the lab today, he told me we are going to have something about 20 readings, and this will make your graph very fine, and you can get most of the outcome out of it. Hopefully by Monday, I'm going to send you the lab sheets. You have to register yourself in one of the 60 groups. Group 1 and 2, they're going to attend the lab from 6 o'clock to 7 p.m. The second group from 7 to 8, and the third one, the 5 and 6 is going to be from 8 to 9. So what's happened is that group 1 is going to do the shake and sieve. The other one is going to be the shear test. When you finish, you are going to change your places, and in 1 hour, you're going to have 2 experiments. You are going to work in a group. You can you will have actually the same readings, but simply the submission of the report is going to be individual. And this actually is saving your right, because maybe if you're going to work in a group that one guy is going to do everything, the partner will do nothing. So that's why, well, I'm encouraging the group work, but once again, to share the knowledge, but not submitting the same report. Okay, so as I mentioned once again, that the powder sample, this is the powder sample, is going to be placed in the holder, and the movement of the sampler holder is going to cause a shear between the powder sample and the sample of the hooper wall, as you can see in the figure number 1. To determine the wall fraction coefficient, which is what the fraction coefficient simple. You did that in many of the subjects. What the simple of the fraction of coefficient? Coefficient of fraction. The mu. Okay. This mu value will give you another indicator, what we call the angle of the wall fraction. So also the movement can cause the shear internally between the powder samples, so we're going to make it for the internal shear. So in case number 1, we check what will be the wall coefficient of fraction. The other one is the internal coefficient of fraction. We're not going to do this one next week. We're going to do the wall fraction test. And that's what we're going to use in the next design procedure. So once again, this is a close look. So in the wall fraction test, the fraction is going to be measured between the sample and the wall, which is the plate cover. In the second case, the internal shear test is going to be done to check what will be the fraction internally between the powder sample layers. Now, from the wall fraction testing, this will be the equation you are going to use to find the value of the mu. The F, the force you are going to apply, and the N. So N is the normal force you are going to put, and the F is the force you are going to use to move the cover lead. If you are going to divide the F by the N, you will get the mu. So I should change this one. Actually, we have to unify that. This will be delta. Okay, the delta. Yeah, well, because I used different reference last time, and I forgot to change this one. So anyway, you'll notice that because the term is going to be the same, the angle of the wall of fraction, which is delta W. So once again, as we mentioned in this test, we are going to apply the normal force, which is going to be the N, and I'm going to use a horizontal force, which is the F. This one and this one. If I go and simply divide that by this one, I will get the value of the mu, which is the coefficient of fraction. The coefficient of fraction, okay, is the tangent of the phi, which is the angle of the wall of fraction. The arctan means inverse tangent. So the inverse tangent of a mu, which has been calculated from this equation, will give you the value of the phi or the delta wall. So if I'm going to make a graph between the normal stress I'm going to apply and the shear stress I'm going to get, the angle between them is going to be the delta W. Okay, so this is the wall angle value. I should change it. Actually, I thought I changed it, but I don't know what's happened anyway. So after a number of values have recorded, the wall yield locus is going to be identified by the plotting of the shear stress against the normal stress. I posted that in the video for the assignment number 1, right? When we made the Moore circle. So the angle of the wall of fraction, yeah, I changed it here, is the angle that is going to be formed when the line is drawn from the origin, okay, connecting all the points in the way. And the powder technology usually is going to express mu as the Hooper angle as a fraction of the angle of the wall of fraction of the delta W. So delta W is going to be the tangent inverse of mu. Now, this delta W is the same as phi here, but I forgot to change this one.
So it should be a straight line?
As possible.
Right.
As possible. Okay? But you always have to start from the origin. Because usually 0 means 0. Okay? So you're going to have multiple points. You make the curve, then you get the what they call it, the it's not a slope actually. No, the line is going to be passed by most of them, or at least in between most of the points. Okay, so do you remind the angle, the Hooper angle, the delta wall? We may well, it's already been published many measurements about that. So the angle of the internal fraction can be either 30 degree, 40 degree, 50 degree, and 60 degree, as you can see in these lines. This will be the wall fraction angle, and this is the Hooper angle from the vertical. So you calculate the delta W, then you go to, for example, it's going to be 20. and the angle of the internal refraction, for example, is going to be 30. So 20, go to the black line of 30, then you go down to find what will be the Hooper angle from the vertical. Again, to have an example for this one, we're not going to use this chart. The chart we are going to use, I already prepared a copy for you. It's available in the in this week folder. You have to print this one. You are going to use it for the assignment, and you have to bring it with you to the final exam. The same one is going to be used.
The design chart.
Design chart, something similar to this one. I'm going to show you. It's on the next page.
Yeah. So
What is that? Yeah. Anyway, yeah, it's there already. Yeah. So so this actually shows you the same thing. In the case of the fuel flow, this one is for the massive flow, fuel flow as well. What's the massive flow one? So we talked about this one last week. We said we can have the shear test either for the Jenkins shear test, when we're going to have the slip between the material particles, or we can use the ring shear test, which give you actually the same material, the same results. But in this one, we are going to have the rotating table instead of the sliding table. Then you have to do the circle. These are the points you got, the shear test and the normal stress. You make your line between them, and you make two circles to give you the value of the critical stress and the maximum stress. So common causes of the failure of the silos are the shock load during the arc collapse. So what's happened that the arc starts to occur by mistake. Someone inserted a stake, tried to break it, then a big vibration happening, boom. Now, what we reach is that the forces in the silo is going to be different. So it will collapse from one point because all the forces are going to be concentrated there. Also, depending on the cylindrical walls and the overpressure due to the change in the cross section.
Is that all sheet metal? Huh?
All made of sheet metal. Some of them are made of concrete.
Oh yeah. Okay.
Okay. The stresses we have, sorry. Yeah.
Yeah. Before it was mentioned the word vibrations that could cause
Yeah.
caking and stuff.
Yeah.
So would
No, vibration don't cause the caking.
in between the small particles are moving in between.
That's the internal. Oh, what do you mean? The vibration?
Yeah. It was mentioned somewhere back there. Some small vibrations.
Cause what?
To everything to get stuck.
No, we didn't mention the vibration.
Okay.
We said the pressure. Okay. You're talking about the time constellation, right?
Yes.
Yeah. We said that the humidity, the temperature, the pressure, and other the temperature.
What about environmental conditions?
These are the environmental
Like,
conditions.
things like wind, for example. Would it affect anything?
Well, because it's cylindrical, so it wouldn't affect.
Okay.
Unless if you're going to have tornadoes, this will be something different. Okay. So the stress we have in the hooper and the silo. Now, just imagine you have a big water tank and you fill with the water, a cylindrical shape. What do you think will be the stress we are going to have in? Where will be the maximum and where will be the minimum?
Maximum at the bottom.
Yeah, and the minimum at the top? No, the minimum is going to be after the discharging. At the discharge point, after the releasing of the fluid, everything will be zero for the pressure. It's already leaving. So you will see the curve for that. So the cylindrical section is controlled by the Janssen equation. And in the case of the stresses of the hooper and the silo for the conical sections is going to be use the radial stress field process. So usually the stresses we're talking about is the pressure that the material exposing to the wall. So if I'm going to take a section and have this differential equation, okay, so we are going to consider that we have in small portion of the material an equilibrium of the forces on the differential element DH, this part. Okay, so the PV multiplied by the A is the vertical pressure acting from above. The pressure multiplied by the area is the force. The gamma multiplied by the area multiplied by the G, which is the 9.81, multiplied by the delta H, the difference in the height, is going to be the weight of the material in this red element. The PV plus the delta into PV multiplied by the A is the support of the material from below. The material supporting the material to push it up. And the tau multiplied by pi multiplied by the diameter multiplied by the difference in the diameter of the material is going to be the support from the solid fraction on the wall. So if I'm going to continue the differential balance on the cylindrical storage bin, I don't want to take you to the mathematics side. We're going to end up with this equation. Yes?
What is gamma and tau in the equation?
Sorry?
Gamma and tau. Can you go back to the previous slide? What is gamma and tau?
How is shear stress?
Gamma.
Yeah, gamma is the shear stress. And which one is the other one?
Tau.
Tau. Yeah, that's shear stress between the wall and the material. That's the internal between the particles. And this is between the material and the wall. I think we talked about this one last week.
Not gamma.
Ah, okay. So here the differential between two shear forces. The gamma is going to be the internal shear force, and the tau is with the wall. Okay, so we are going to end up with that the P value, the pressure we are going to have on the wall, using the Janssen equation, is going to be equal to the rho multiplied by the G multiplied by D divided by 4 mu K multiplied by 1 minus exponential of minus 4 H mu K divided by D. I know this is very complicated. It's much better to use it like this way. So that's the equation of the stress in the cylinders using the Janssen equation. Because this will depend on the particle of the material we are going to store. We are going to have two different methods.
Rho is
The density.
yeah, but what is this in the top? 0. Oh.
Yeah, well, of the material. Okay. The original density, because we don't consider, yeah,
No comparison.
exactly.
Yeah.
Okay, so that will be the equation. And of course, to make your life easier when you do, if you are going to have something similar to that in the exam, is do it by part. So you do what will be the exponential of minus 4 mu kz divided by d, and then you subtract from 1, then you multiply everything by this part. So this will be the shape of the pressure we are going to have in the silo. So you can see that we're starting at the minimum value at the top. The only pressure we have here is going to be the pressure of the air. Then we will go to increase the hydrostatic and the bulk solid pressure inside. And at the exit, we are going to have zero pressure because everything is going to be released to the outside.
But this is when it's discharging.
Yeah,
But
it's
when
after
stopped-
the thing. Yeah. Which one? Sorry. Before that,
Yeah.
this will be the much of the. Essentially, there's no stress at the outlet, and this go for discharge of the device. If we're going to have pressure from the outside, this will prevent things from happening. So we should get zero pressure here to allow the thing going on the other side.
Yeah.
But just one step before that, you are going to have higher pressure, as you can see. Okay, now we are going to have design example. We are going to have a large welded silo. Is that something similar to the question you have in the assignment? Yes. So we have a steel welded silo which have 4 meter in diameter, and the height is 20. This need to be built. The silo has a central discharge in the flat bottom, and we have to estimate the pressure on the wall of the wall bottom of the silo if the silo is going to be filled with the plastic pellets or water. Now, which one have more density? Now you can see that the density of the plastic pellet is going to be 560 kilogram per cubic meter. What the density of the water? So definitely the pressure of the water is going to be higher than the pressure of the plastic pellet. So now we have been given the rho and we have been given the delta W. Now, what do I have in the equation here? Do I have any delta W? how am I going to use the delta W here to find the mu? So tangent of this angle is going to give you the mu value. We have the rho, the G is constant, the diameter is given. I will tell you how to get the value of the K, and well, it's KZ. So everything should be possible.
What is K and what is
We'll get it now. So what's given is that the equation, the D is 4 meter, H is 20 meters, and the G is equal to 9.81, and the density is 560. So we got that, we got this one, we got this one, the 4, the K is not known yet. Okay, and the H is giving mu will be calculated, K divided by the diameter. So how to get K value? First, that's how we get the mu value. The K is the Janssen coefficient, and usually it's assumed 0.4. Always. Okay, now we got all the parameters and we start to do the calculation. So once again, that's the given things. So the steps first for the Janssen equation, for the silo of the circular cross section, the diameter and the height are given in the problem statement, and the coefficient of the wall fraction is obtained by the inverting as the mu is equal to tangent of 20. The K Janssen coefficient is assumed to be 0.4, and the Janssen coefficient can vary with the material, but is not often measured. I know you have the answer in the next page, but now I would like you to take these parameters and let's start to calculate the answer with your calculators, even with the phone. Do you have exponential on the phone?
Yeah.
Okay. So let's try to do that because this will be a good practice. You have to do the same equation once again in the assignment. So let's practice on this one. Write down the parameters.
And the full equation, it's over 4 mu k GC and
Yeah,
it's
the same thing. G and K same. Okay, it's not Z by itself. It's K Z.
Small z.
Yes.
And k JC. JC.
JC is same. The gravitational acceleration
9.8.
9.81.
So it's 9.81 over 9.81. Can you go back to the equation?
Oh, you mean the percentage?
Not the,
Yes. I'll go to
not the
this one.
percentage. Yeah,
Yeah.
KJC.
Yeah.
No, yes.
I will show you how to use this value.
Oh,
But what is Z there?
Z is KZ.
No, it's
K
KZ.
small z.
But there is not K there?
No, it's the same.
No, I just removed from here.
Yeah, so it's K.
Mhm.
Yeah, but the JC we don't have in the equation.
I will show you that. Now, I will hide that, get the parameter, I will give you the equation, and you have to start to think about it. Oh, come on, you have paper in front of you, write it. No, because I'm going to hide this one. Did you got all the parameters and the equation? Use the above equation. Rho GD divided by 4 mu K multiplied by 1 minus the exponential of minus 4H multiplied by mu K divided by D. The D is 3.6. Actually, the D is 4, sorry. The D is 4 and it's not 3.6 because I changed the example. This mu is 4, D is 4, the H is 20. This D is from last year example. Okay, so I will hide that. Yeah, K is 0.4. And I will show you the answer.
I don't know. It's E. This one. This one. This one. What's this one? Yeah. Oh, this E. EFX. Yeah. So this is. I guess this.
Okay, now for the GC, it's incorporated as 1, which is how many kilogram per meter, well, a specific gravity of the water. Yeah, I hide it. I wanted you to give me the answer before I get to show it to you. You got the answer? Okay, what do you want? Which one? The H is 4, the rho is 560, the K is 0.4. What else? You got minus 65? No, that's wrong. That's wrong. Okay, now, as I told you, find this value first. Find this value, then do it is exponential, then subtract it from 1, then multiply by that. So you start from here, finishing to the other side. Okay, now the trick with this equation is you start from the, when you look this way, yeah, you start from the left, from the right, going toward the left.
I got something so big. I guess I can say.
How much you got?
55,000?
Yeah, why not?
I don't know.
Yeah, why not?
Oh, alright.
Yeah.
But I'm not sure because I'm not sure of the
Now,
exponential.
just imagine, it's 20 meters height and full with material. What do you expect the pressure to be?
This is
Yeah,
in
that's
Pascal.
Pascal.
That's Pascal. Oh, yeah, it's logic.
Yeah.
35
Yeah.
kilopascal.
Yeah.
Kilopascal.
Megapascal is so big. I don't know. That's I will double check.
Yeah, yeah.
Yeah, that's.
Okay, so I see that. How many of you got 36,000? Okay, that's good. You're on the right path. Okay, so I'm going to show you the slides now. Did I fix that? Yes.
Yes. No, I did mine myself, but mine is so I did mine. This.
What is that? Ah.
Should be 0.0.
Okay, so we had all the parameters, and we're going to substitute now to the Janssen equation. We said once again that the rho is 560 multiplied by 9.8 multiplied by 4 divided by 4 4 multiplied by mu multiplied by 0.4 multiplied by 1 with specific gravity, a specific expression of the mass. But you can simply cancel this one. Multiplied by 1 minus the exponential of minus 4 mu k divided by d. Now, once again, we said that you start from the right side, find this value first, find its exponential, subtract it from 1, then you multiply by 560 by 9.81 by 4 divided by 4 multiplied by the tangent of 20 multiplied by 0.4. And this will give you the value of 35,668. This should be comma, by the way. Pascal, or what equal to 5.2 psi. Okay. Now, find the value of the normal structure wall. We apply the Janssen assumption that the P of the wall, the pressure on the wall, is equal to the pressure we have calculated, the vertical pressure, multiplied by the K value. So simply, the P of the wall is going to be equal to 36,000 multiplied by 0.4. Okay, and this will give you 14,267 kilopascal.
It's 14 point.
It's not point, it's comma, but anyway. I should put K here anyway, yeah. Now the other assumption is if the solid was filled with water instead of the granule solids, the pressure depth H is going to be given by the P is equal to the rho GH divided by GC. That's the simple equation you got in the fluid dynamics, right? You remember this one? GC is going to be equal to 1.
Roger, yeah.
Yeah, that's the specific gravitational, yes. So what we're going to get is 1,000 for the water density multiplied by the G of 9.81 multiplied by 20 meters divided by 1, and this will give me that the pressure, the vertical pressure, is going to be simply equal to 196,140 or 28 psi. Now, how many double is that? Is 13 times greater than the normal wall stress calculated in the case number 1 of the plastic pellets, and that's due to the wall friction exerting the vertical upward forces on the granule solids. Now, how to calculate how much we can add material to be stored in this volume? Now you can see that this one actually is going to be divided into 3 sections, right? So what will be the total volume here?
The 3 sections.
The adding of the 3 volumes we have in these sections. So what we have is the stored volume is the volume of the conical section below plus the volume of the parallel section plus the volume resulting from the surcharge filling. Or the volume is going to be pi multiplied by 24 divided by the tangent of theta multiplied by the d cube minus the dc cube, the diameter of the conical shape, plus the pi divided by 4 d squared multiplied by the h, plus the pi divided by 24, the tangent of beta. D is diameter of the bin itself, dc diameter of the outlet. We are going to have the height of the cylindrical section is h, theta is the half angle of the conical section, and the beta is the surcharge angle of the material free surface. Okay, that's the beta. The height of the cylindrical section, h, can be given usually, should be preferred to be 0.385 multiplied by the diameter. Okay, or we can simply calculate it by the 1.274 multiplied by the mass divided by the d squared rho of the material. If the surcharge space is going to be, the top is going to be considered, then the h total of the material is going to be the h of the height in the cylinder plus 1.15 d. All the equations here are going to be accurate at theta is equal to beta and is equal to 30 degrees. Now, usually the height should be always more than the diameter, but less than 4 times of the diameter of the bin you are going to have. Now, we talked about this one, but once again, we have to remember that. Now, we talked something about the critical stress and the stress applied. Now, if the value of the stress is equal to the critical, there will be no flow to happen because the critical stress is equal to prevent the value of the stress we apply for the material, so no flow will occur. So the condition we have for the flow condition, the sigma 1 should be more than the sigma critical. In worst case, it should be equal to. And that's what we call the KAS or the CAS. And we're going to talk about the critical amount of the stresses required to make the flow. We said that we have two types of the Prince hoopers, which can be either the pyramidal shape or the conical shape. We're going to learn about how we can calculate the minimum diameter outlet for each case. How many of you have laptop today? All of you? Good. So we'll try to solve some of the questions we have in the assignment if we are going to have time today. So also we can have the chisel outlet for the hooper. We can have the wedge, or what we call the plane flow, where in this case the width of the outlet is going to be less than 3 times of the length. Once again, the conical hooper, the square opening, the chisel type, and the wedges and the pyramids are all possible. But in this class, we are going to concentrate on the conical hoopers and the wedge type hoopers design process. Okay, that's just repeating important things. So you know what the equivalent diameter. So that's in case if I'm going to have this square opening, we calculate the value of the diameter. Then we start to calculate accordingly what will be the width and what will be the height. So in this section, yes?
The previous slide, please. The cylindrical flat bottom circular opening, where can you give us an example as to where this will be employed?
Well, we're going to employ this type.
Where would you use such a design?
The flat one?
Yeah.
It's very common.
For like.
Well, most of the farm silos are flat.
So wouldn't the material stay at the flat bottom?
Yeah. I'm going to show you that in the video lecture I'm going to post, because we're going to add a devices inside which is going to push the material to the center, and we start the discharges from there. Okay. So have you seen the screw inside the screw conveyor? So it's going to be something similar to that. It's going to rotate, center in the middle, start to rotate, bring the material to the center, where we're going to discharge it outside.
Is this from the last piece?
Yes, that's true.
Yeah, that's for the flat bottom type. Okay. Okay, now in this section, we're going to learn about the determining of the minimum hooper outlet size. You can see that this will be highly influenced once again by the density and the characteristics of the material we're going to store in. So the force acting on the powder material stored in the hooper tend to first compact the powder, as we understand earlier, and this will reduce the bulk density, and the shear stresses in the material tend to make it flow. So Jenkins equation flow factor is the flow factor, the FF, and we are going to learn how we are going to find this value, is equal to the compacting stress divided by the applied shear stress. Now, I think you remember something from last week when we talked about the flow factor. We said that if the flow factor is going to be more than 1, we're going to have the flow to happen. If it's going to be more than 1, less than 1, we're going to have the cohesive. So the material will start to stuck if the value of the FF slope is going to be less than 1. More than 1, up to 10, is going to be free fall in the case of 10. Okay, so that's the condition we should have, that the value of the FF should be always equal to or less than 1. So that's what we described last time. The material is going to be hardened if we're going to have the value of the FF is going to be less than 1. And it's very cohesive instead of less than 2, cohesive minus less than 4, easy flowing less than 10, and free flowing is going to be more than 10. The standard we use to design the outlet is actually going to be based on the shear test of Jenkins, which is going to be the ACM D6128/16. I tried to find a copy of this one and send it to you, but actually it's still copyrighted and we didn't have a copy in the library. But anyway, I'll try to find something and send it to you later. Now, this graph is used to design the chart of the symmetrical slot outlet hoopers. Okay, and this is an example we have here. So we understand how to find the value of the wall fraction in degree, right? We said if I know what the value of the mu, I can find what the value of the wall fraction in degree, the delta wall. Then I will know what will be the wall fraction curve, and I'm going to use it against the flow factor curve. So what's happened, for example, if my delta wall is going to be equal to 22 in this example, and my delta, for example, is going to be equal to 50, that's how we are going to do it. Move horizontally until we are going to intersect with the line of the delta, then go downward. You will find what the value of the theta, which is the angle of the semi-included wall. From here, I will go up to the same value of the delta I'm choose here. For example, that was 50 in this example, so not 30. So going here, intersect with the 50, going down, find the value of the theta. Going up once again, intersects with the 50, then go to the left, to the right, sorry, to find the value of the FF. I'm going to show you an interactive method to do that in the example. So once again, we said for the Janke equation of the flow, we said that the value of the FF is equal to the sigma 1 divided by the sigma A. If I find what the value of the FF from this chart, I will be able to calculate what the value of the critical value of the stress to make the flow happening through the minimum diameter. This one is going to be for the conical hoopers. Now the same process actually. You go to the right, intersect with the delta you choose for the wall fraction curve. You go down, find the value of the theta. You go up once again, intersect with this value, with this dashed line. Go to the right, you will find the value of the FF. So this one is for the conical outlet, and this one is for the symmetrical slot, the rectangular shape. Okay, so we talked about the effect of the storage time on the minimum outlet dimension. As we are going to take it for keep it for longer time in the hooper, you will need bigger diameter to empty it. Because the constellation is happening, the density of the material is going to increase. So this will affect everything we are going to design. Okay, now once again, these are the same diagram, but actually, as I told you, I send you these two charts. You have to print it and keep it with you. Even in the final exam, you're going to bring a copy. So each lecture, we're going to have design process with chart. I try to separate the charts for you so you can print it and bring it with you. Well, sorry, if you're about to do something there with the phone, so stop doing it now. Or at least watch the phone, but don't talk a lot, okay? Because we cannot hear each other. Okay, so that's what we talked about, the CAS and how to find this value. This is very important to find the value of the CAS to calculate what the value of the minimum diameter we should have for the hooper. So the intersection of the value of the 1FF we got from the previous chart. Okay, so this line had the slope of the value of the 1 over FF. And we are going to make another curve for the material flow function according to the value we are going to get for the sigma 1 experimentally and the value of the sigma C, the experimental one. Then the intersection will give me the value of the CAS, which is the critical applied stress value. So the stress in the outlet of the hooper may drop below the value of the CAS if the opening is going to be too small. Hence, the outlet opening size must ensure that the applied stress exceeds the value of the CAS. We always should go above the critical value. Hey guys, don't chat in the class. Okay, and the correlation resulting that the outlet size of the CAS are going to be provided. So this is another example for the diagram, and actually this was the assignment 2 years ago. And I'm going to show you how we can simply make the sketch of these two lines, because you have to do it in the question number 1 in the assignment. So we said once again that the flow function is going to be the value of the critical value of the cats is going to be increased as the time is going to pass. That's why we are going to need bigger diameter for the outlet of the hooper. The value of the diameter is a function of the cat's value. So the D is going to be equal to the H theta multiplied by the cats divided by the raw material multiplied by the G divided by the GC. And the H value here, H theta, will depend on the angle we are going to find from this chart. The theta, the semi-included angle in degree. And that's depend on the outlet we are going to have. This equation is going to be for the circular outlet. Well, that's the, what do you call it? Once again, it's the, no, it's, I just said it a few minutes ago. What did I call it? The specific gravitational of the fluid. Yeah, it's 1 for water, and usually they use it as universal, 1. Okay? Yes? I'm sorry. Yeah, that's for the flowing of the particles. Yes, that's different. Okay, so the H is going to be constant, which is a function of the Hooper angle. Typical value for the H value is going to be something about 2.4. But it's better to calculate it as long as you can find the value of the theta from the chart. This will give you more accurate value for the H. Usually it's going to be more than 1 for the wedge hooper and more than 2 for the conical hoopers. And we will see what will be the other equation if I'm going to have the wedge hooper outlet. That will be the H value, H theta, in the case of the symmetrical hoopers. And after we are going to find the value of the W, the minimum W, you can find what the value of the length. Simply is going to be 3 times. And just remember once again, this will be the minimum. So for example, for the diameter, if you are going to get it as 0.123 meters, you're not going to ask them to make it exactly this diameter. You will take it to, which one is going to be the standard one, for example? 0.15, right? Which is going to be more than the minimum diameter you're going to have. So this will be a function for the H theta, as we mentioned earlier. Usually it's going to be more than 1 in the case of the square shape, more than 2 in the case of the circular, and it can be vary from 1 up to 1.5 in the case of the rectangular outlets. Now, once again, just remember that these are the minimum dimensions of the outlets to ensure the mass will occur, the massive flow to occur. So in the next section, some of the correlations are going to be given for the estimating for the flow, throughput of the solids through the opening we are going to have for the bin. The larger opening may be used for the greater throughputs and still maintain the massive flow. In a practical, the design angle theta is going to be reduced by 3 degrees as a margin of the safety. Now you will see, for example, here we will get 25 degrees. So in the real life, I'm going to use it 22. But now in the assignment, just keep it as it is. What you get from the chart, use it directly in your calculations. We are going to have this example. After you are going to have 20 minutes of break. Is that good? You can use the...
Too much.
Too much? Oh, you want to leave earlier?
No, but
15?
20 is too much. I don't mind if we stay later, but
Okay, 15 minutes? 10 minutes, okay. It's not an auction, right? Okay. So now we are going to learn how to use these charts to find parameters to calculate the minimum, to find the minimum diameter outlets. So we said once again we have to do some measurements and we have to do the calculations. So we're starting with the shear stress. Yield stress JYL is the plots from the certain material yield. The data shown in table number 2 determine the wall slope and the opening size to ensure that we are going to have massive flow in a conical hopper for this material, assuming that the bulk density is going to be 1,300 kilogram per cubic meter. That's the table we have. That's something similar somehow to the table you have in your assignment question number 1. But the other one is more details. We have 3 tests, so we can have more lines, we can have 3 more circles, and this one we maybe need to do 1 graph. So what's happening here that the shear stress of the internal refraction curve shown as following. The first sample, we added stress of 2.4. Oh, actually, we should start from here. We added the stress of 1.3. We got the sigma c is equal to 0.78. When we increase the load to 1.6, we got the sigma c of 0.85. The sigma 1 increased to 2 kilopascal. The sigma c is going to be 0.91. And well, the 2.4 kilopascal, the sigma c was 0.97. This is the first test. Then, okay, now this is internal refraction. That means the test device I use is the one would have 2 halves. So we measured the fraction between the particles of the sample itself. Then I remove the second half and I start to check what the fraction between the sample and the plate of the cover. That's the test number 2, wall fraction measurements. We did 2 run. The first one, the normal n value was equal to 2. The value of the shear force tau was equal to 0.689 kilopascal. Then I increased the load to 3, more weight. I got the value of 1.03 for the shear force. For the effective angle of the internal refraction delta, the curve I got was the rise in the delta y in kilopascal was equal to 1, while the delta x was 1.73. Now, I got here, that's mean what I got is delta y and delta x. I have something like that. And of course, between them, I'm going to have a curve. And this curve should have a slope. And this slope is what? The mu value, right? And from this mu value, I can find the tangent of it. I will get the delta wall. That's a good hint. So that's something similar to the table you have in the question somehow. But as I told you, the video I posted, the second one, not the more circle one, is give you many hints about the question number 1. If you have any other question, you can send me an email, or maybe we can set a certain time where we're going to have online discussion or something like that. So first I'm going to find the value of the delta. The tangent of the delta is going to be the delta y divided by the delta x in the diagram I have, right? This is the tangent of the line. So it's going to be 1 delta y divided by 1.73, and the tangent of the delta is going to be equal to 0.578, which is the mu value, right?
If you take the arc tangent of this, you end up with the.
No.
Exact. Now this tangent, if I go to tangent inverse, I will get the value of the delta w. So the delta w is going to be equal to the arc tangent of this value, and we're going to finish up with the 30 degree. That's the delta. Now I would like to find, I have 2 values for the shear force and the normal force. So I can simply, 2 is going to go to 0.7 something, and for the 3 I'll go with the 1.13. So put these 2 points, join from the origin, make a straight line again to get the wall fraction angle given the data of the points plot as in the figure. So sorry, this is the delta and this is the delta wall. So from which we can see that the data are going to be linear. The angle is going to be easily found from the rays run as before. So this will be the delta y divided by the delta x. I can find the angle here. So the tangent of the delta wall is going to be delta y divided by the delta x. And this will give me that the value here is going to be 0.3433. And that's mean that the delta wall is going to be equal to 19 degrees. Now, do you recall the charts we had? On the vertical x-axis, I have the delta wall. And on these lines, which are going down, I have the delta. Now, this will be on the vertical axis of this chart. And this 30 degree is going to be on the line going down. I will make the intersection, find the theta, and find the value of the FF. And from there, I will do my rest of the calculation to find the value of the cast. Then I can find the diameter of my pen. Now, that's the chart I have. The wall fraction in degrees. That's the delta W, 19 degree. It's not this value. I'm going to make put the new value. And these are the delta, the wall fraction curve. I got the 30 degree. So this one is 30 degree. So simply, that's my delta W, 19 degree. I can use this line and this line. The dashed 30, and this is the straight 130. Now what's happening is that from the 19 degree, I will make horizontal line, which is going to intersect with this line, then going down. Then I will go up once again to intersect with this one, then go to the right side x-axis to find the value of the FF. So that's how we are going to start. 1. Then I will go below. I found the theta. Then I will go up. Then go to the right. I got the FF. Okay? So just remember the sequence once again. From the calculation, the experimental calculations, measurements, I got the value of the delta W and the delta. I have to choose two lines for delta because we have the one going from the left to right, and I have the one going from the right, from right to left, and I have the one going on the opposite direction. So I have to choose both. The dash one is going to be used to find the value of the FF. The left one is going to be used to find the value of the theta. So sketch a line. This is my intersection with the 30 degree delta. Going down, I will find the value of the theta, 28. Then go up, intersect with this line, then go horizontally to find the value of the FF, 1.84 or 1.85. So the theta is equal to 23, and this one is equal to 1.84. Okay, now I got the value of the FF, so I can find the value of the 1 over FF and sketch the orange line, which is going to have the slope of 1 over 184. Okay, so the orange line had the slope of 1 over 1.84. And these points are the points I got from the table. Okay, this on the x-axis, these are on the y-axis, and I had these 4 points. I sketch a line between them, then made the orange line, which have the slope of the value of the 1 over FF. Then these lines are going to be intersecting. Okay, now their intersection, if I'm going to sketch a horizontal line, this will give me the value of the cast. So this is just like step 1, 2, 3. That's the only thing you have to do. Just follow these steps. Yeah, you have something similar to that in the assignment. But in the assignment, you have to make the more circle. You have to find other parameters. Watch the video, and it will explain everything for you.
What is MFF?
Which one? The the
4
the
points.
the flow function, the
Okay.
material flow function.
Okay.
Okay, so the sigma with sigma c with sigma data are going to be plotted to obtain the material flow function, the MFF, and the FF value is used to plot the value of the 1 over FF line, the orange one, as shown in the figure, and to obtain the critical applied stress CAS value from the intersection of these two lines. Okay, so this will be the CAS value 0.81, 0.83. Okay, so this is the CAS value. Now I got the CAS value. Now, do you recall the equation for the B minimum, which is the minimum diameter we should have for the thing? Now, we got the theta as 28. Now, we said in the practical life, I should use 3 degrees less than the value I got. So it should be 25 degrees. But I'm going to keep the 28 in this example because I don't want to confuse you. For the value for the diameter is going to be the h theta I can get from here. We said it's usually 2.4, but I'm going to get the accurate value because we calculate the value of the theta. Why not use this equation directly? I got the CAS. I know the density. I'll multiply by the G. Just ignore the GC. I can simply rewrite all the equation for you and send it to you, so you don't have to get confused after the equation later. So first, the 28 divided by 60 is equal to 0.48 plus 2,
2.48.
hopefully.
6.
467. I was that close. Okay, then I'm going to apply this value here, multiply by the CAS, which was 0.83 kilopascal, multiplied by 1000. Well, this is just for the specific thing, just to remove the things. Okay, so 1000 Pascal over kilopascal. This for unit conversion because this one in kilopascal and this one kilogram meter over second square is going to be in Pascal. So I had to change everything to Pascal. That's why I have the 1000 here. Okay, then multiply by the GC, which is 1, and the minimum diameter we're going to have is 0.16. Now, this is the minimum diameter. So if I'm going to make a design for something like that, you have to consider that you are going to have the time consolidation after a while if you're going to store the material for a longer time. So what you're going, 0.2 is going to be the option you are going to have. So 20 millimeter is not that bad. If you're going to go for 25, this will be better. Okay, now shall we start the things from the beginning? Now we had a test, we got these values. Now just remember it was 1,300. Okay, so what we got first is we did the internal fraction test. Okay, the shear stress for the internal fraction. And to recall this one, we have 2 layers of the materials. We added the force on the top of it and start to slide it with the horizontal force. So there will be internal friction between the particles of the material itself, and then that's what we got. That's the stress I added, and that's what the stress resulting to push the things horizontally. Now, simply you have to do that because you cannot measure the friction value directly. You cannot do that. So do you think, actually that's what's happening even if you're going to do the fraction, coefficient of fraction for the solid parts. So you put a particle on the surface and start to add the force on it and push it, check the resistance and check the value of the mu. Okay, so we got this value for the sigma 1, this value for the sigma c. And then I remove the upper ring and keep the surface and of the plate to be slide on the material sample to get the value of the wall friction measurements. We took just two values and we finished up with getting the normal force at 2 kilopascal will generate the shear force of 0.68 between the plate at the top and the material. And the 3 is going to generate 1.03. Now, this will be too useful for us to find the value, this one, to find the value of the delta wall, because this is the friction between the wall and the material. This one is the internal friction. Now, the angle of the internal friction value delta can be simplified because we have the delta y and the delta x. So we can find the tangent of the delta, then we can find the value of the delta itself. So these are the steps. Tangent of the delta is equal to the delta y over delta x, and this will give you the value of the tangent, and the arc tangents will give you the value of the delta of the wall. The effective angle of the internal fraction. And the wall fraction angle itself, by having these 2 points, sketch a line from the original point, and simply I will calculate what the value of the angle here. Because I can find the slope, tangent inverse, I will get the value of the delta W. Now, I know the delta W. I know the delta. I know we should have a conical outlet. So I will go for this chart. Now, the second chart is for the symmetrical. This one is for the conical. I know now what the value of the delta, 30 and 30. And this is the value of the delta wall. So sketch the first line by indicating delta wall. And this delta, horizontal line, intersect going down, find the theta, going up, intersect going right, get the FF. So we got theta and the FF. The theta will help me define the H theta, and the FF will help me to find the value of the slope of the 1 over FF curve. So that's what I'm going to do. Sketch 1 over FF curve, and the 4 points I have for the internal fraction will be used to sketch this line. They're going to intersect here, horizontal line. This will give you the value on the yield straight axis for the cast value, which is the critical apply stress to ensure we are going to have the massive flow for the at the exit. Now, I got the cast value of 0.83 kilopascal, and I know that the equation to find the value of the diameter minimum is h theta multiplied by the cast multiplied by the density multiplied by the g. Put these figures first. The h theta is going to be equal to 2.467. Apply it here. Change unify the units. You have to remember that. Now, of course, you remember that the kilogram multiplied by the meters divided by second square is equal to what? Newton over meter square. Okay, so simply we're going to have this one in kilopascal. We have to change it to pascal, which is a Newton over meter square. And we're going to have at the end that the meter is going to be the unit for that. 0.16, and this will be the minimum acceptable value, and you have to go over this one by all the cases. So hence the mass flow of the conical hooper at the minimum diameter of the opening is going to be 0.161 meters. A margin safety, a semi-included angle going to be reduced by 3 degrees, and the hooper design angle should be used at 25. That's in practical. Don't use it in the exam or the assignment.
Oh, really? Yeah.
That's just for the practical, okay? For as a safety factor, because this will simply going to increase the things. Now, after I found out what the outlet diameter, I can simply check what will be the rate discharge from the hooper, because this is once again very important. I will know what will be the how many kilogram per a minute I'm going to have, or kilogram per second. So we have numerous methods to do that, depending mainly on the minimum practical the particle diameter. If the powder should be different from the bigger part, like the sands or the gravel or whatever the thing is. So for the coarse particles, where they are going to have the diameter is more than 500 microns, there are two equations. The first one is the Bevel equation for the funnel flow, and we have Johansen equation for the massive flow. Usually you would like to have massive flow. For the fine particles like the powder, one must consider the influence of the air up on the discharge rate, because the air will try to prevent the powder from flowing down. So first we are going to start for the massive flow using the Johansen equation. Okay, so Johansen equation derived from the fundamental principle, and this has been found in 1965, published at the ASME journal in 1966. M dot, the massive flow rate, is equal to the density of the material multiplied by the area of the outlet. Now we found the minimum pin diameter, and we can find the area. Multiplied by under square root of the B multiplied by G divided by the 2 plus 1 plus M multiplied by the tangent of theta. Now let's see what are these things. Now we know what the rho, know what the A, we know what the theta is. Well, I changed the B right here. Yeah, actually I changed the B. I think the B is going to be the same as the rho. So theta is going to be the semi-included angle of the hooper. M dot is the discharge rate. The rho is the bulk density in kilogram per cubic meter. G is the gravity acceleration. The A is the area of the discharge outlet. M is going to be 1 for the conical hoopers, 0 for the symmetrical slot hooper. Now, for the Johansen equation, depending on whether the conical or symmetrical slot opening, the hooper remaining parameters of the equation are given in table number 3. The B, the A, and the M. Now, definitely this will be the area of the circular shape. That will be the area of the rectangular shape. The M is going to be equal to 1 in the conical hooper, 0 in the symmetric slot hooper. The B, in the case of the conical hooper, is going to be diameter of the outlet, or is going to be the width, not the length, the width of the symmetrical slot hooper. Now, for the funnel flow, we can use the Bevel equation. Now, this one is quite different because actually this has been found back in the late 70s. That's been something about 15 years after Johansen. So he said that the M dot is going to be equal to 0.58 multiplied by the rho multiplied by the G up to power 0.5 multiplied by the D minus K dP up to power 2.5. Now the D is small is the diameter of the particle, and that's something we can predict by the sieving process, as you remember. The rho is the bulk density, G is the gravity acceleration, K is a constant, and this is usually something more than 1.3, less than 2.9. Usually the 1.4 is going to be used if no discharge rate data are being available. D is the outlet diameter for non-circular outlets, and the hydraulic diameter is going to be used, which is going to be equal to the area multiplied by 4 divided parameters in the case of the symmetrical shape. Now you know what the hydraulic diameter is, right? How many of you did air conditioning before? How many of you doing air conditioning now? Good. Now, usually when you do the design for the ducts, you calculate the diameter, so that the duct is not circular. Because what's happened is, we have something called the equivalent diameter even for the non-circular shapes. And we have an equations like this one, which can tell you what the relationship between the equivalent diameters and the parameters of the shape you have. I'm not going to flow. Thank you. Okay, so for the fine particles, if it's going to be too fine like the powder is.
Oh, nothing. Sorry.
Oh, I saw you
No,
doing
no, no,
that.
no.
Okay. For fine particles, you're going to be less than 500 microns in the maximum diameter for the particle. They tend to flow the slower by the factor of 100 to 1000 than the practice by the Johansen equation, because we said that the air will try to prevent the things from flowing down because it's too light and small. So the reason for this effect is the air drag on the motion of the particles is much greater for the fine particles. So
Okay.
I'm not going to give you a powder in the final exam. Okay, so Carleton gives the expression for protecting the velocity of the solid as this equation. I'm not going to read it. Okay, so simply that's what we're going to have. So the m dot is equal to the rho multiplied by the A multiplied by the VO. How to find the VO? You have to use this equation to find the VO. You got that? Yeah, you have to take, well, look. So definitely I'm not going to give you that in the final exam. I don't want to fail you.
Who came up with that?
This guy, Carleton. Okay.
He's been trying.
Yeah, call him. He died.
Go him.
Okay, so this is the equation in case if you are going to have small particles. Actually, this equation is very popular in the industry of the pharmacy because they're dealing with the powder all the time. So if you have one day need to use this one, actually I can send you some links about the software which can do this calculation very easy. Now, a discharge rate example. Now, what we are going to have here is an equation. Give you a relationship between the yield stress and the applied stress. And this equation is not going to be just simple linear equation. It's going to be an exponential equation. Anyway, now this is example once again, and you may have it as a question in the final exam, or you may have it as a question in the assessment. Do I have one in the assessment similar to that? Maybe not the exponential equation, but it's going to be the same process. So what's happening here that we did the experiment with the shear box of Yankees and on the particle catalyst to give the family of the yield locus as this slope. That's a relationship. Given that the bulk density is going to be 1000 kilogram per cubic meter, and the particles and the wall fraction angle is going to be 15 degree. From a design chart silicone, do design mass of flow hooper for the material. And if the average size is going to be 100 micrometers, calculate the discharge flow rate passing through the discharge opening. So the second case, we have to use this equation. So the procedure of the design, now we don't know what the value of the theta or the FF. We have to find that. We don't have data as we had before to calculate what the value of the delta, but we have the delta W. From there, from having the FF, from the parameter we are going to get from the equation, we can find the CAS value. Then we can calculate the value of the minimum outlet diameter. Then we can do the calculation for the discharge rate. So simply this example is a combination of the previous example, but instead of having the parameters from the test, we have the equation. So we can simply say that if the sigma is going to be equal to 1, what will be the value of the sigma c? So we can simply extract the data we got from the test by using the equation relationship between them. So the calculation of the semi includes angle theta, and the flow factor can be simply found by simply the effective angle of the internal fraction is given as 40 degree, and the angle of the wall fraction is given as 16 degree. By using the following chart, we will find the value of the theta and the FF as 30 for the theta, and the FF is going to be equal to 1.5. Now, this is the angle of the theta we have found, as you remember. Okay, so it's the slope angle we are going to have there. So totally this one will be 60. We said that this will be minimum as 45. So now we are going to calculating the value of the CAS. This is a relationship given to us. So from this relationship, we are going to assume the value of the sigma in kilopascal, and this will give me the value of the ys, which is the sigma c. So I can make simply, according to the equation, where I can find several points will be created to draw the value of the FF curve. And the intersection of the curve with the line through the origin having the slope of the 1 over f will give the value of the critical applied stresses gas as we had done earlier. So for the MFF, I will assume the value for the sigma, and this will give me the value of the ys. Okay, so sigma 1 is going to be equal to 0. The value of the ys is going to be equal to 0. 1, 1, 2, 1.36. 3, 1.639, and at 4 is going to be 1.866. Now, for the 1 over FF, the sigma 1 is going to be 0.40, 1 is going to be 0.667, 42 is going to be 1.334. Okay, by the way, I'm not going to tell you how I found these values. I would like you to try, go home, search, and try to get, okay, now this one is obviously we're going to apply the value of the sigma, and we got this value. I would like you to find how did I find these values. Okay, actually this example is available online. Okay, so this, well,
Too late.
yeah, too late. Okay, so this one was using the equation we have, and this one actually, damn.
We're gonna try
Okay,
at home.
yeah, don't try it at home. Now, actually, this one will simply going to be equal to 1 over FF that we found it, 1 over 1.15, multiplied by the value of the sigma 1 we suggested, then we got the value of the 1 over FF curve. Now we can sketch the two curves, okay, and we're going to have the intersection between them, and we can find the value of the CAS to be 1.39 kilopascal. What else? Now we know the theta is 30 degree. You can find the h theta. We found the value of the CAS. We know the density. Then we can find the value of the B minimum. So the B is equal to the h theta multiplied by the CAS divided by the rho multiplied by the G. And simply the h theta is going to be equal to 2.5. And the minimum diameter is going to be equal to 0.355 meters. Now I got the B, and that's why I need to find the value of the m dot. Okay. Okay, now I'm supposed to have the solution later here. Anyway, now we got the B. I will leave this one for you. Okay, now I don't have the answer. Now you got the value of the B, and I would like you to complete the other two. The calculation of the minimum outer diameter has been found. Just do the calculation of the discharge rate. I would like you to use the easiest one is going to be your Johansson equation. Use the Johansson equation. Yeah, let's do it now. Write down the Johansson equation. Yeah, you wrote down the equation. We'll go to the given data. So first, conical hooper is what we're talking about. So the B is going to be the diameter we calculated. The area is going to be the area of the circle with this diameter. And the M is going to be equal to 1. Okay. What's the problem?
I got the previous
Yeah.
example. He's been doing the previous example. The
Ah,
data.
you still do.
No, no, no.
Okay. No. The data is going to be this one. Now let's try also with this equation. So let's make a comparison between the value we're going to have from both equations. So just remember this is a fluid flow. The m dot is going to be equal to 0.58 multiplied by the rho multiplied by the g up to power 0.5 multiplied by the d minus k dp 2.5. Take the k value as 1.4. That's the other question. We're going to make a comparison between both equations. That's multiplied by.
Ah, times.
Yes.
Oh, oh my
I will change it to points. Okay, if you like to. You feel better now? Good. Okay, now the particle diameter, let's take it as 500 instead of the 100 we have in the question. So both are going to be for the coarse material. Okay, so now we have two equations. Just remember the K here is going to be 1.4. Okay, and the D particle for both, well, this in meters. So when we said 500 micrometers, you should change it to meters. That's mean you have to multiply it by 10 up to power minus 6.
500 yeah, micrometers.
Micrometers, yes.
5 to the minus 3.
Yes. 0.5 times 10 to the minus 3.
Yeah.
Yes.
Now, so leave this equation. Now, that's what we got here. First, what we need is, do we need? The density, 1,000.
Rho.
The density is 1,000. You'll need it in both equations.
Water.
No, it's not water. It's not water. Okay, so that's the theta. And this one we said is going to be 500 micrometers. Now we go to the next, we don't need it.
Why do we need this?
We don't need in these equations.
How do we
Now
define
what?
theta?
Theta is 30. You found already or something?
Theta is 30, yes.
30.
So this will be the diameter we are going to use. What else do we need?
Uh,
That's it?
This one
That's
is
it,
B. No, we need DP.
Yeah, we said it's 500 micrometers.
Oh,
How many times I have to say
sorry,
that?
sorry.
Sorry?
From the table,
From the
chart.
we got it from the chart.
Yeah.
Okay, now we go for both equations.
And now go for both equations and let's see what the difference between them. Yeah, it's micron.
Yeah.
What is it?
Yes. I can't do it on my phone.
Ah. Now, definitely in the exam, you have to bring calculators because you cannot get your phone into the exam, right?
And this one. Because it's,
Oh, but that's good. You put all in one. That's good.
What is the D here?
Which one? Yes, deep.
This
Yeah.
how
This
calculate
We
the
said it's 500
exponents?
micrometers. It's 500 micrometers, so change it to meters. It's going to be 10 micrometers. You have to unify everything and the same unit. Oh, good.
for what?
Then divide by 4.
That's not scientific calculator.
Yeah.
Change it to a scientific area.
Yes. Pi square.
If you don't want to divide by 4, then square the base. Yeah.
What do you think by yourself? It's not everything, right?
And 0.0, yeah.
Pay more for this chair.
0.01. No.
Well, I encourage to do the practice in the class because what's happening is that if I'm only going to give you the example and you are just following up with that during the practice, when you come to the assignment, you are sitting there by yourself or you're working in a group. And when you're working in a group, if one of the guys don't have to do the things, the rest will only get to copy the method without understanding what's going on. So that's why I changed the parameters, which make everyone have to do his own solution.
No, it's 30.
What's happened previously with this subject that many of the students got good marks in the assessment, but when they read the final exam, they had to do their own solution and they found too many problems. What happened last semester, last year, I told the students to do the assessment as the quiz. So we were sitting here, give you 1 hour, give you the question, do the solution, and submit the answer. But what happened is that the hall was twice the size of this one, and I had 120 students or 140 students all talking at the same time. So they drove me crazy, and I decided to stop doing that. So you have to find an example. You have to draw down stuff. No, I don't get to be that guy. So
We don't have this.
sorry. I don't know the answer.
What if it's square root of 1.2?
For the 9 plus square, so what do you think? Square root of what? So have you got the similar answer from both equations? Have you got almost same answer from both equations?
I can't do it on my phone.
You can't do it on your phone. Download the smart calculators.
Which one?
Yeah, but
Yeah, but x to the power 2.5 you can't do it. Yeah.
so what is your answer? 1 to 2?
2.8.
So you got almost the same answer from both equations?
No. We have the same
For
answer
the
for
first
one.
one.
Ah, okay. Okay, let's go for another
So what is the
5 minutes.
Oh, you're gonna do it.
I'll do it together, then I'll do it separately for you in a second. What's the stage
CS points, yeah. 355. Don't forget it's 500 times 10 minus 6, yeah.
I was supposed to tell you this one earlier, but actually, do you know where the fire exit in this room?
Here.
Yeah. So in case of emergency, leave from here. Well, actually, we should say that in lecture 1.
How much you got?
You got something similar?
155? No.
Within, yeah, okay, good, yeah, because actually we said that the first equation was for the mass flow, the other one was for the other type, which flow? I forgot.
Which one do you usually?
Not counter flow. We are not talking about the funnel flow. Yeah. Okay, so that's why we had this difference, and it actually is going to be good practice if you try to use this equation with the particle size of 100. I know it's quite challenging, but you can find an answer with that by using the log of the thing, the logarithm. Now we go for another example, and this example is in British Standard because, as I told you earlier, that we're still having using actually the IP unit. So, and this one, once again, we're going to try to calculate the discharge rate. So it's having that an engineer wants to know how fast the compartments of the recycle rail car will fill with the polyethylene pellets. If the hooper is going to be designed with 6 inches point of 10 outlets, and the car have 4 compartments and can carry 180,000 pounds. The bulk solid has being discharged from the massive flow silo and has 65-degree angle from the horizontal. And the polyethylene is going to have a bulk density of 35 pounds per cubic feet. So the challenge you're going to have here is about the unit. And just remember that this angle 65 should be divided by 2, because this one is from the horizontal. So for one compartment, total we have 180,000. We had to divide it by 4. So we're going to have 45,000 pounds in each one. Since the silo have massive flow, we're going to use the Johansson equation. 6 inches for 10 pipes is going to be 6.36 inches in diameter, and this will be the value of the minimum diameter. The weight is going to be equal to 35 pounds per cubic feet multiplied by the pi 4, divided by 4, multiplied by 6.36 divided by 12 to change it from the inches to feet, square, multiplied by 32.2, multiplied by the 6.36 divided by 12, divided by the 4 tangent or 25 up to 4.5. And the W, the flow rate is going to be 23.35 pound per second. So the required is 45,000 divided by, that's the time, the total mass divided by the massive flow rate, and this will give you something about 32 minutes to empty the whole compartment. In practice, that's too long, so we can simply get a bigger outlet will be a better choice to reduce the time required to empty the compartment. Okay, and I would like you to have this one as a home study, and that's something similar to one of the final exam questions we had earlier. Let's give you the first example. So we have to find the height, h, the L, and the volume of this silo. So we know how to do the calculation for the silo total volume. The bulk angle of the repose is equal to 35 degrees. The sliding angle of the repose is equal to 45 degrees. Diameter of the silo is 2 meters. The weight of the product in the silo is 70,000 kilograms. And the heat head space is 10%. And the bulk density of the product is going to be 700 kilograms per cubic meter. And the volume of the conical part can be found by using this equation. Now, after we calculate what the volume here, we want to discharge the silo within 30 minutes. We have to calculate the required discharge diameter, and you are going to hear that the Q, which is the flow discharge rate, is going to be equal to the K, D up to power N, giving these values. Diameter of the discharge, and what will be the mass flow rate. So you have an equation, and you have to use this equation to find what the minimum value of the B using the discharge equations we had earlier. Now, I can tell you that you can find this answer online. And actually, I'm encouraging the search because this will improve your research ability, even for the knowledge. And this, because actually, when you find the solution, you will get the knowledge to do that. Okay, and as I told you, these two charts, I've been prepared that on PDF file. And you can print this one, use it in the assessment and the final exam.
What are the dashed lines for? For some random example or?
Which one? This dashed line?
Yeah.
For you want to find the right
To find the FF, you use the dashed line.
No, the small ones with the arrows. The ones answered.
Oh no, no, yeah. This was an example. Yeah,
Okay.
that's an example.
Yeah, yeah, yeah.
Yes, yes, both. Yeah,
That's just kind of a direction of how
Yeah.
it works.
yes.
Yeah.
But you don't have to look like that to solve it. I print it for you vertically. Okay, so do you have any questions? Now, once again, I don't have to repeat what I did for the assessment because simply I posted two videos. The first video is to do the Moore circle using the graphical method. The other one was describing each question and with some hints about the solution. If you still have any questions, send me an email and I can prepare another video for you. And because if you have a question, maybe the other person didn't thought about it, but it's going to be very necessary to know what's going on. So every question will be, well, multiple question will be one video, so everybody will get the benefit.
So the assignment with the assessment we need to like submit is like a PDF file.
Yes.
So we need to scan it?
If you are going to do it hand calculate by hand, you have to scan it, but it should be very neat writing. Oh, guys, before you leave, just remember that next week we are meeting at level B4, building 11,
When
Next week?
next Friday, the coming Friday, week 3. Yeah. No, no. I'm going to upload the groups, and you have to register yourself in the groups. Group 1 and 2 from 6 to 8. 6 to 7, sorry. Group 3 and 4 from 7 to 8. 5 and 6 from 8 to 9. Yes. You have to come with time, yeah, so you can do this one. Because actually we have limited number, about 10 students going to be on each experiment. Sorry, 20 students. So I don't want it to be too jammed. Every 30 minutes we are going to try. Yeah.
Where is this again?
B4. Building 11. I'm going to post that and I'm going to send you the reminder email every day until you are going to go to the school and tell them that he accused us.
Something for this assignment, we don't need to make like a report style thing with abstract and like introduction and
Just
For the lab, right?
no.
That's
No, for this one. No, just answer the questions and that's
I
it.
had one subject like this.
Do you want all the report discussion?
Ah,
The full question to answer and we got D is equals to B, yeah?
mhm.
Equal?
Yes, yes,
Same.
yes.
Thank you.
You're welcome. Let me turn off the recording before we talk.
forgot my phone.
Oh, you're charging here.